Okay, so in this video I'm going to have a look at a question that came up in 2015, paper 1, question 6 at higher level Leaving Cert. It involves Donna, who is arranging a loan and is examining two different repayment options. So we're just going to have a look at Bank A first of all, which will charge him a monthly interest rate of 0.35%. And we've got to find, corrected three significant figures, the annual percentage rate that this is equivalent to. So we've got to change this 0.35 monthly rate into an annual rate. So what we're going to do, we're going to use this formula here. So this is F is equal to, F is the final value, P is the principal, 1 plus I is the rate, this rate here as a decimal, and then T is going to be our time period. So let's have a look. What we're going to do as usual here is we're going to say, let's put in €1. If we put €1 into this account here, what would our final value be? So what would F be if we put in €1? So we got to work out what this would be. Now you don't have to use 1, you could use 100. Just use nice figures that are easy to use. So 1 is usually handy, and then, or you could use 100 either. So I normally use 1. So we have 1 plus, now our interest rate here, our monthly interest rate here is what we're going to put in here, and that's 0.35%. But we want that as a decimal, so it's going to be 0.0035. Now because this is our monthly rate, our time period here is going to be it's going to be in months. So we want to know we want to convert months to years, if you like. So we're going to put in 12 months here. So we put in €1 at 0.35% over 12 months. What will that amount to? So if you work this out, what you'll actually get is our F here will be equal to 1.042818. Now that's our final value. So €1 will amount to €1 and 4.2818 cents. So in other words, our actual rate for the year then would be 4.28%. This is our APR. Remember, we use APR when we talk about loans, our annual percentage rate. So this is our yearly rate, and 0.35% was our monthly rate. Okay, so let's move on to the next part of this question, which is this one here. Let me just move this up a little bit. Okay, so in this particular case, Donna looks at Bank B, and this will charge him an equivalent, an APR. This is our annual rate now of 4.5%, and we want to find, corrected three significant figures, the monthly interest rate. So in the first part of the question we had a monthly rate, we converted it to an annual rate. Now we have an annual rate and we want to convert it back to a monthly rate. So again, we use the same formula again. So we're going to use F, our final value, is equal to our principal times 1 plus our rate as a decimal times T. Now what we're going to do here then is again I'll use €1 here, and on this side then we'll have, because this is our annual rate, that's going to amount to €1.045. So if I put €1 into this account at an annual rate of 4.5%, the final value after 1 year will be 1.045. Okay, so now remember, we want a monthly rate now, so we are now looking for this I here, and again our time period is 12 months, so we want to find I now, or this is our annual rate here. Okay, so how do we do this? Well, the first thing we've got to do is notice that you've got a power of 12 here. So to get rid of this power of 12, we've got to get the 12th root of both sides. So really what I'm going to do is take our 1.045 here and get the 12th root of it. You can do it this way, or you can do it this way here. It's the same thing. So this is the 12th root of 1.045. That will leave me on the right hand side then with 1 plus I. Let's just move this 1 over then. That will give me 1.045 to the power of 1/12th, or the 12th root of 1.045, minus 1. That will give me I here, or my annual rate. Okay, so sorry, this is my monthly rate. Sorry, I should say this is 4.5% was my annual rate. I'm trying to find a monthly rate. So if you do this, if you get the 12th root of this number here, and whatever you get, subtract 1, what you'll actually end up with is a monthly rate then. Monthly rate of 0.367%. So when you actually do this here, you'll get 0.00367. That's what I will come out as, and then as a percentage then just multiply by 100. Okay, so that's how you convert from an annual rate to a monthly rate, and a monthly rate to an annual rate. Now let's have a look at the next part of the question. So let me just move this up again. Okay, so now we have Donna, who's borrowing 80,000 euros at a monthly interest rate now of 0.35%. So this came up in one of the previous questions, so we might use that in this question. So anyway, this is fixed for the term of the loan from Bank A. The loan is to be repaid in equal monthly repayments over 10 years. Okay, so the first repayment is due 1 month after the loan is issued, and this idea of 1 month after the loan is quite important in these type of questions. Calculate correct to the nearest euro the amount of each monthly repayment. So how much does he have to pay back every month in order to repay this loan over 10 years? So I'm going to do this two different ways. The first way I'm going to do it is using what's called the amortization formula. So that is this formula here. It's in the maths tables, so you should be able to find that there. So it is A is equal to the principal. So this A here is the monthly repayments. P is the principal, in other words the loan amount, and you're going to multiply that by I times 1 plus I to the power of t over 1 plus I again to the power of t minus 1. Okay, so this is the formula we're going to use. It's called the amortization formula. It's used to work out monthly repayments on a loan. Now there is a derivation for this formula. I may do it in another video, but for the moment we'll just accept it as being correct, and we'll use it. So all you've got to do here really is just stick in all the values that you have. So A is going to be our answer really. It's the amount of each monthly repayment. So P is the principal, and our principal was the loan amount, which is 80,000 euros. Now in here then we're going to put in I, which is the APR. In this case it's 0.35%, but put it in as a decimal, so it's 0.0035. Now we've got 1 plus, again I, 0.0035, and to the power of t. Now remember, this is over 10 years, but we're looking at a monthly interest rate here. That's the rate we're using here. So we've got to do 10 times 12, which is 120 months. So it's to the power of 120. This is all over 1 plus I again, so it's 1 plus 0.0035 again, and this is the power of 120, and then from all of that we subtract 1. And that's really it. After that, it's really just calculator work. You've just got to, maybe do the top line, write down the answer, do the bottom line, write down the answer, and then multiply by this. Try not to just stick everything into your calculator and press equals and hope it works. Sometimes you need to stick in extra brackets here and there, so just be a little bit careful with that. So do it in steps. So really what you end up with is 80,000, and just on the top line here, so it's 0.005322 96, and then on the bottom part here we got 0.520846. Multiply all that out then and you get 817.59 euros. That's the amount that Donna has to pay back every month in order to pay back 80,000 euros over 10 years. Now it says calculate correct to the nearest euro, so that's we'll just do that a little bit as well. So that's approximately equal to 818 euros. So Donna has to pay back 818 euros every month for the next 10 years in order to pay back this loan. Okay, so let's do this in a different way now. Let's just have a look at using the sum of a geometric series in order to do this. So let's have a look at that. Okay. Now, first thing I'm going to do is just I'm going to do a timeline. I like to do this with these type of questions. So I'll just show you what way this works. So we're going to take this here as now this is time 0. This is 1 month later, so I'll call that T1. We'll do another one here. We'll call this one T2, so that's 2 months later. And there are loads of months in between, and let's do one out here. So let's say this is time 119, because remember we were talking about 120 months. And then we've got another one here, so we call this T120. So this is 120 months later. Okay, so let's see what happens here. We Donna has to pay back a certain amount every month. So he's paying back an amount here, a certain amount here, a certain amount here, a certain amount here, and a certain amount here. Actually, come to think of it, he doesn't pay anything back here because it said in the question that his first repayment is at the end of the first month. So I'm just going to take this bit here out. So he actually starts repaying here 1 month later. Okay, so really what happens here is 1 month later he pays back he pays back a certain amount, and we're going to try and find that out. We're going to work out the present value of that amount. Then 2 months later he pays back A again, this amount that we're going to work out. We're going to work out the present value of that amount. And so on all the way along. And then down along here then we've got this A amount. He pays back a certain amount A 119 months later. What's the present value of that amount? So we're going to work that back to the present period of time. And then finally he does, remember he pays back at the end of each month, so he's going to pay back A here as well. So we're going to work this back, find the present value of that amount there. And the reason we're working out the present values of all of these A's is because remember that a loan amount is the sum of the present value of all future repayments. So in other words, when you add up all of these, the present value of all of these A's, it should equal to 80,000, the loan amount. So what we're going to do is get the present value of each of these. Now remember, again, if we look at our formula, we had f is equal to p times 1 plus I to the power of t. Now really, p is our present value. P is the present value. That's what we want to work out. So in other words, if we take p here is equal to, and f is the final value, or in this case each of these values, it's going to be a here really. So instead of f here I'm going to put in a. So that's going to be a over 1 plus I to the power of t. This is what we're going to use here to work out the present value of each of these a's. Now if you take the first period here, he pays back an amount a here. So what is that? Well, it's going to be, I'll do it in a different color here, let's say green here. Okay, so we're going to pay, he's going to pay back a certain amount 1 month later, 1 month from now. So what's its present value? Well, its present value is just this here, so it's going to be A, the amount that he's going to pay back, over 1 plus I. Now remember, I in this case is 0.35%, so that's going to be 0.0035, and that's going to be to the power of 1 because we want the present value of this here, of this amount here, A, and this is 1 month into the future, if you like. So what about the second one then? Well, it's going to be exactly the same as this. It's going to be A over 1.0035. This time it's going to be squared because we're looking at 2 months here and here, 2 months, and so on all the way down along. When we get to here, we end up with A over 1.0035, and how many months is this? Is going to be, well, if you look here, from here to here is 1 month, and that's T1. From here to here is 2 months, and that's T2. So from here to here is going to be 119 months. So that's to the power of 119. And the last one then has been, you're looking at 120 months, so it's just going to be A over 1.0035 to the power of 120. Now I'm going to write all of these down here. Remember, all of these added up together should add up to 80,000, because remember, the present value, the sum of the present value of all future repayments is equal to the loan amount. So in other words, when we add all of these up, they have to add up to 80,000. So let's just write that out. Okay, so really what we should end up with is 80,000 euros is equal to, first one was A over 1.0035. The next one was A over 1.0035 squared. The next one was A over 1.0035 cubed, and so on. And then out at the end here we had A over 1.0035 to the power of 119, plus the last one was A over 1.0035 to the power of 120. Okay, so we can see on the right hand side here we really have a geometric series, the sum of a geometric series. So what I'm going to do first of all, I'm going to just factorize out, I'm going to factorize out the A. So that's 1.0035 plus 1 over 1.0035 squared, plus, and so on out here to the end, 1.0035 to the power of 119, plus 1 over 1.0035 to the power of 120. So all I've done really is just take an A out of each term here. Now if you look at this here, within the square brackets here we've got the sum of a geometric series. So remember, well, I've just run through that. A here, if you just look inside the bracket here, A, the first term of our geometric series, is 1 over 1.0035. The common ratio, what do I multiply this by to get this? What do I multiply this by to get my next term? What do I multiply this by to get this one here? Well, it's just 1 over 1.0035. Because I have this, I'm squaring it, then I'm multiplying it by 1.0035 again, and so on and so on. So if I multiply each term by this here, I get the next term. So this is my OR, common ratio. How many terms are in this sequence here, or this series here I should say? Well, there's 1, 2, it's whatever the power is here, that's the power 1, 2, 3, 4, 5, 119, 120. So there are 120 terms. Okay, so now I have everything that I can put into my sum of a geometric series formula. And remember from previous videos, Sn, the sum of a geometric series is A times, now you can use 1 minus r to the power of n, or r to the power of n minus 1. In our case r is less than 1, So I'm going to put the 1 first. So it's 1 minus r to the power of n over 1 minus r. So that's the formula I'm going to use. Now let's just put in the values then. So we have a, well our a is just, now actually what I'm going to do here is put in the entire equation. So remember, I'm going to put in this entire equation. I'm going to include the a, and I'm going to include the 80,000 as well. And I'm going to put this part here in our sum of a geometric series in here. So let's do that. Okay, so I have 80,000 euros is equal to a times. Now a is 1 over 1.0035, 1 minus r to the power of n, 1 minus my r, which is 1.0035 as well, and that is to the power of n, which is 120. Okay, so that's the top line, and on the bottom line then I'm going to put in 1 minus r, which is 1 over 1.0035. Okay, so that's a rather big calculation to do, but just do it in steps and it should work out nice and neatly for you. So 80,000 on the left hand side, we've got a here. Now when you work all of this out, you should be able to work that out. Work it out in steps, as I say. Work out this bit, subtract it from 1, multiply by this, and then divide by this here. But what you end up with is a multiplied by 97.8489137. So that's really it. And then all we got to do now is just work out a, so I'm just going to divide across by 97.8489137. So I end up here with a equal to 817.58. Now again, we've got to just round that to the nearest euro, so it's approximately equal to, I should say here, 818 euros. And that's exactly what we got in the first part of the question, but this is using the sum of a geometric series to work it out. And that's it for this video.